In the first part of Unit 7, we took a look at classifying different types of chemical reactions. In the second half of Unit 7, we're going to take a look at the mole and molar relationships as how they relate to mass relationships as well. Okay, so our first objective is going to be review the definition of mole and convert between the number of moles and the number of particles of a substance. So the mole, as my 10th grade chemistry teacher said, I don't think I remember anything else he said other than the fact is a mole is a number. So it's just a number. It's a counting unit that's used to count when you have many particles or many of the same type. So or things that are really small. We can't see atoms, we can't see molecules, but we can see grams of atoms and grams of molecules. But how many particles is that in a certain amount, right? In a certain grams. We can actually use the mole to count any large number, or really small number. We could use moles to count the number of rats in New York, the number of roaches in a building. It's just a counting number. And just like a case of cans is 24 cans, a gross of pencils is 144 pencils, a ream of paper is 500 sheets, and a dozen is 12, right? And we use those to count. So if anyone says to you a dozen, you know automatically that number equals 12. So the mole is similar to that. And it's a counting unit that we called Avogadro's number. And just like a dozen has 12 items, Avogadro's number, or the mole, has 6.02 times 10 to the 23 items. And we can use it to count small particles such as atoms, molecules, and ions. And notice this is a really large number, and it was named after an Italian physicist. So we can see how large this number is. Here we are at 10 to the 5 is the average college tuition. We are at 10 to the, 10 to the 7 is the population of the earth, which is in billions. 10 to the, 14 is the distance from the sun. And 10 to the 21 is the amount of water in the world's oceans. So if I have 1 mole of an element, that means that I have 6.02 times 10 to the 23 atoms of that element. So what does that mean? That means that I have 6.02, if I have a mole of carbon, that means I have 6.02 times 10 to the 23 atoms of carbon. The same goes for sulfur, right? Any of these samples. I can say that I have a mole of aluminum, and that means that I have 6.02 times 10 to the 23 atoms of aluminum. Same as looking at moles of sulfur. I can also say that I have 1 mole of water, and then that means that I have 6.02 times 10 to the 23 molecules of water, right? Same goes for a mole of vitamin C. That means that I would have 6.02 times 10 to the 23 molecules of vitamin C. If I'm looking at a mole of sodium chloride, then that means I have 6.02 times 10 to the 23 formula units, meaning this is 1 formula unit, 1 sodium, 1 chloride ion per unit. You know that whenever we're using a conversion factor, you're going to put the unit that you're looking for on top when you're multiplying by the information that you're given, right? Next, we're going to take a look at gram to mole conversions. We've already taken a look at converting between the number of moles and the number of particles, but we are going to now take a look at converting between the molar mass, the number of particles, and the number of particles of a substance. So what is the molar mass? It's the mass of 1 mole of a substance. This is just a more it's a mass of 6.022 times 10 to the 23. That's just giving you one extra sig fig. It's not necessarily. And it's also what we call the molecular weight, and that's only for molecules. The molecular weight or the formula weight in grams. So for this video, we're going to take a look at using the molar mass to convert between the mass and the number of particles of a substance, and convert between mass, moles, and the number of particles. I guess that's the same learning objective. No, converting between the mass, moles, and the number of particles within a substance. So I mean, like, how many ions are there, or how many atoms there are in a formula unit or in a chemical formula. So the molar mass is essentially just the mass of the atoms in a compound, and we simply just change the AMU with grams per mole. So the molar mass of ethylene, which has two atoms of, one unit of ethylene would have 2 carbon atoms, 4 hydrogen atoms, right? And the mass would end up being 28.0 AMU. However, if we're looking at 1 mole of ethylene, that 1 mole of ethylene has 2 moles of carbon and 4 moles of hydrogen per mole. So we now have grams per mole as our molar mass. So the molar mass is numerically equal to the molecular weight or the formula weight. We're just now going to use grams per mole. So that just means I have a certain number of grams per 1 mole of substance, or we can write that as 1 gram or grams per mole, okay? So given that we have the molar mass of a substance, let's say if I know that 1 mole of methane is equal to 16.05 grams of methane, then I can have a conversion factor. If I'm given the number of moles, I can determine the number of grams by putting grams on top. And given the number of grams, I can determine the number of moles by putting the number of moles on top, or 1 mole on top. This next problem has a few steps to it. You are asked for how many molecules of this pseudoephedrine chloride are in a tablet that contains a dose of 30 milligrams of this decongestant. So what we're given is that we have 30.0 milligrams, and we need the number of molecules. So what is our plan? What is our roadmap? Well, what do we have? Well, we've got milligrams, and we cannot compare milligrams. We can't compare grams, milligrams, and moles. So we've got to convert our milligrams to grams. And we can't compare grams and particles without first converting to moles. And then we need to determine the number of particles, which is the number of molecules. So we have 3 steps here, and at each step we're going to have a different conversion factor. So the first one, we need a metric conversion, and that's going to be our milligrams to grams, and we need grams on top and milligrams on the bottom. So we know it's 10 to the 3 milligrams per 1 gram. Number 2, we need to get from grams to moles, and here we're going to use the molar mass and put moles on top and grams on the bottom. And for number 3, we need to get from moles to molecules, so we're going to use Avogadro's number and put 6.02 times 10 to the 23 molecules on top of 1 mole. Now, if you calculate the molar mass of this compound, you should end up with 201.69 grams per mole. All right, so we're going to solve our problem by always starting what we were given. 30 milligrams, 1 gram is 10 to the 3 milligrams. Notice that our milligrams were canceled out. Then we need our molar mass, which is, and we're going to put moles on top. 1 mole is going to be 2.01 times 69 grams. And then, so our grams cancel out. And then we know that there's 6.02 times 10 to the 23 molecules per 1 mole. And our moles cancel out. Remember, you're going to put this into the calculator as, in your calculator, you're going to put in 30 times 6.02 divided by 1,000, which is the same as 10 to the 3, divided by 201.69. And you leave your power of 10 till the end. And what you get here is you're going to get 0.000895, and if we have 10 to the 23 divided by, if you had 10 to the 20, well, I put 1,000 into the calculator, so you would get times 10 to the 23. So forget what I just said there, because I used 1,000 instead of 10 to the 3. So I end up with 0.000895 times 10 to the 23. And moving the decimal place 1, 2, 3, 4 places to have correct scientific notation, 8.95. And if I move my decimal place over to the right and my coefficient gets larger, then my exponent is going to get smaller by the same number. And I moved over 4 spaces, so that's going to be 10 to the 19. And I need 3 significant figures. So that would be my answer. 8.95 times 10 to the 19 molecules of pseudoephedrine. Okay. We can also take a look at the number of moles of an element in a formula. If I look at a chemical formula, the subscripts not only specify the number of atoms in one molecule, but it also specifies the number of moles of each element in 1 mole of the compound. Right? So 1 molecule. So if I have the chemical formula for aspirin, it's C9H8O4. That means that I have 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen in 1 molecule. But it also means that I have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen in 1 mole of this substance. Right? So I can look at this formula and not only consider 1 individual molecule, but a whole mole of this substance. And a mole would, the mass of one mole would be the mass of all of those atoms together. So, what can we say about this formula in moles? Well, for 1 mole of aspirin, we can have many different conversion factors. Well, I can say that for 1 mole, there are 9 moles of carbon, or for 1 mole, there are 8 moles of hydrogen, and there are 4 moles of oxygen per 1 mole. And notice that the conversions are interchangeable depending on what we're looking for. You're going to put the moles of the atom on top if we need to find out the number of moles of the substance. We'll put the number of the moles of the substance on top if we're looking for the, if we're given the number of moles of each atom. Okay, let's practice taking a look at this problem. This question asks how many atoms of oxygen, how many atoms of oxygen are there in 0.15 moles of aspirin? Well, as for any problem, we're always going to first start with what we're given and what we need. We're going to write a plan to convert from moles of the compound, moles of the element, and we need to find out, we need to end up with the atoms, and then we're going to use equalities to help us figure it out. So let's think about it. Where are we starting? We were given 0.150 moles of aspirin, and we need the number of oxygen atoms in that given number of mole. So remember I told you whenever you see atoms or molecules, that's a signal that you're going to have to use Avogadro's number. So what are we doing? We're given the number of moles of the compound, right? But we need to end up with the number of oxygen atoms. Well, we can't compare moles of compound to oxygen atoms. We've got to figure out a way to get from moles of compound to the moles of oxygen. So we've got to determine the moles of oxygen. So we've got 2 steps here. At step 1, what are we going to use to determine how to get, what conversion are we going to use to get from the moles of the compound to the moles of oxygen? We're going to use the molar ratio from the formula. And that ratio is, I've got 4 moles of oxygen, 4 moles of oxygen for every 1 mole of aspirin. Right? And number 2, we need Avogadro's number to get from the moles of oxygen to the number of atoms of oxygen. So I'm going to put 6.02 times 10 to the 23 oxygen atoms on top of 1 mole of oxygen. So let's solve our problem. So we want to know the number of oxygen atoms, and that's going to be equal to, remember we always start with what we're given, 0.150 moles of aspirin times our molar ratio. I've got 1 mole of aspirin, and there's 4 moles of oxygen atoms in that 1 mole. And 1 mole of oxygen is going to be 6.02 times 10 to the 23 oxygen atoms. So notice that I kept all my names in my calculation, so I know that I'm canceling out properly. Moles of aspirin are going to cancel with moles of aspirin. Moles of oxygen cancel with moles of oxygen. And then I'm left with the number of atoms. If you do the math now, you're going to end up with 3.61 times 10 to the 23 oxygen atoms.